Introducing BrainBridge, the world's first revolutionary concept for a head transplant machine, which uses state-of-the-art robotics and artificial intelligence to conduct complete head and face transplantation procedures, ensuring smooth outcomes and faster recoveries. Because head transplants require high speed, precision, and efficiency, BrainBridge utilizes advanced high-speed, high-precision robotic systems to speed up the process, eliminate human error, prevent brain cell degradation, and ensure seamless compatibility. The head transplant procedure involves removing a person's entire head, containing the brain, from their current diseased body, and attaching it to the body of a healthy, young, brain-dead donor. Head transplants could provide individuals with severe medical conditions, such as terminal cancer, paralysis, spinal cord injuries, or neurodegenerative diseases, the opportunity to have a fully functional body while preserving their consciousness, memories, and cognitive abilities. The neurons are the longest-lasting functional cells in the human body, and according to our estimates, the brain is capable of lasting several hundred years, provided that the rest of the body remains young. The BrainBridge concept involves the use of the integrated robotics platform comprised of the 2 autonomous surgical robots, designed to perform simultaneous surgeries on 2 bodies side by side within a single setup. The complete robotization of the process allows for the surgery to be performed in an environment with varying temperature and pressure. The procedure begins by preparing the donor and recipient bodies. The donor is a brain-dead patient who has a functional body with vital organs in good condition, while the recipient is the patient whose head will be transplanted onto the new body. General anesthesia is administered to both the recipient and the donor. Both patients undergo tracheotomy, with a tube inserted into the trachea to provide respiratory support and facilitate mechanical ventilation. Our proprietary artificial plasma solution is administered to both the recipient and the donor. This solution is designed to keep the brain and body oxygenated, prevent clotting, and allow for safe operation at low temperatures. The recipient's head and the donor body are cooled to approximately 5 degrees Celsius to reduce potential brain damage during the detachment. Guided by advanced real-time molecular-level imaging systems, BrainBridge carefully separates the heads from the 2 bodies with the help of a specialized surgical technique that preserves the spinal cord and key blood vessels. Deep incisions are carefully made around the neck to expose the necessary structures, including the carotid and vertebral arteries, jugular veins, and spine. With the help of specialized AI algorithms, BrainBridge tracks both muscles and nerves during surgery to facilitate seamless reattachment. Next, incisions are made in the trachea, esophagus, veins, and arteries. The blood is then completely drained from the recipient's head to prevent clotting. The recipient's head is then positioned adjacent to the donated body using a mobile platform. BrainBridge immediately connects the detached head to the circulatory system of the donor body, which helps maintain blood flow during the rest of the procedure. It also rewarms the recipient's head and provides it with oxygenated blood. With the help of its ultra-precision surgical instruments, BrainBridge begins reconnecting the spinal cord, esophagus, trachea, nerves, blood vessels, and other tissues. This step facilitates communication between the brain and the new body. The machine utilizes microsurgery techniques and delicate microscopic adjustments to ensure the proper alignment and fusion of the spinal cord and other tissues. To help reconnect the severed neurons, BrainBridge uses a proprietary chemical adhesive, polyethylene glycol, which is applied locally to the spine at the point of fusion. Once the spinal cord is connected, a specialized implant is placed in the epidural space behind the spine over the point of fusion. This implant promotes the repair of damaged neurons and allows the patient's brain to form neural connections with the new body and ensures that the sensory system is restored. It also functions as a temporary backup control device for the donor body. The next step of the operation is a face and scalp transplant where all the muscles, soft tissues, and skin are removed from the recipient's face. The donor's face, muscles, and soft tissues are then precisely transplanted in their place. By transplanting younger donor tissues, the procedure reduces the probability of tissue rejection and offers potential for aesthetic enhancement, particularly in cases where the donor is significantly younger than the recipient. It also restores functionality and structural integrity to the recipient's face and rejuvenates its appearance. BrainBridge then carefully sutures the skin to conceal the complex rewiring beneath the surface. The skin is then treated with a special spray that contains growth factors, anti-fibrotics, and antibiotics. This spray promotes faster skin healing, prevents infections, and reduces scarring in the sutured area. Finally, immunosuppressive drugs are administered to prevent the recipient's immune system from rejecting the donor body. After the surgery, the recipient is carefully monitored in an intensive care unit and is kept in a coma for up to 4 weeks to prevent movement or misalignment of the connected body parts. During this time, the head, neck, and spine are firmly stabilized to optimize the fusion of the spinal cord. Life support systems are utilized to regulate breathing and circulation, while nutrition is delivered through a jejunostomy feeding tube. Gradually, the recipient's brain should regain control over the new body. As the recovery process advances and the patient regains mobility, there will be a need for extensive rehabilitation, physical therapy, and psychological support to help the recipient adapt to their new body and regain motor functions. BrainBridge Headband, which is equipped with a brain-computer interface, will allow the patient to communicate their needs during recovery. Thanks to the power of thought, the headband decodes brainwaves and turns them into text or speech. It could allow the patient to control other devices directly from their brain, granting them the autonomy to execute specific tasks independently throughout their recovery journey. Because of the complexity and unexpected challenges of the head transplant procedure, self-learning algorithms allow BrainBridge to avoid errors and adapt surgical plans in real time, depending on the surgery's needs. It can also improve its capabilities over time by learning from previous surgeries. Learning algorithms can recall past procedures and outcomes to continually refine and enhance surgical techniques and post-operative care. While the surgery is being conducted, the BrainBridge algorithm creates a personalized recovery plan, depending on the progress of the procedure and the needs of the patient. To maximize compatibility and ensure seamless integration, we collaborate with the top experts in generative artificial intelligence, brain-to-computer interfaces, and robotics, with multiple successful projects and hundreds of high-profile peer-reviewed research papers. Over the past few years, we developed the end-to-end approach, which accounts for every single detail, including immune compatibility, brain-body connectivity, replacement of the visual and olfactory systems, and post-operative rehabilitation. BrainBridge, breathing life into new bodies, one head at a time.